Sasaki at the University of Connecticut. Can people in the back hear me? Yes. Okay, awesome. So in general, my dissertation project looks at the evolutionary dynamics of thermal adaptation in marine copepods, small crustaceans. Instead of giving a general overview of all the different components, though, I'm going to talk about part of one of my chapters, which illustrates kind of the central theme of my dissertation, which is that we need integrated approaches in order to explain patterns in adaptation. So we all know that temperature is important for organisms, right? You also probably have some intuitive sense that temperature varies strongly over several different spatial scales, even in a fluid environment like the ocean. Now we can see here from this map of sea surface temperature that the variability in the ocean is dominated by a latitudinal temperature gradient. And this is a relatively stable feature through time, as we might expect to see even within species a corresponding pattern in thermal adaptation as populations adapt in response to this thermal landscape. Now, characterizing these spatial patterns in adaptation is important. It lays the foundation for our understanding of what drives diversification or what drives adaptation in the natural environment. However, I think a robust understanding of those processes requires that we not only describe these patterns, but explain them. And that's where things get really interesting, especially in the marine realm. Right? Many copepod species, that I work with, other planktonic organisms, live suspended up in the water column for their entire lives. That means they can be carried around by currents, sometimes over very large distances. As a result, many planktonic species have large geographic ranges that cover a large proportion of this variability in the thermal environment, as well as they also have, are characterized by high potential for dispersal. That potential for dispersal or connectivity over large distances means that we need to explicitly consider things like gene flow if we're interested in explaining these patterns of adaptation. So I tend to think about adaptation from the whole organism perspective rather than mind-scale mechanisms. And at this level, things like thermal tolerance, the trait that I'm going to talk about today, things like thermal tolerance might be influenced by several different adaptive mechanisms. The two that my dissertation is focused on that I'll talk about in this talk are genetic differentiation and phenotypic plasticity. Right? I don't really spend too much time on what these are, but I do want to make sure we're on the same page. Genetic differentiation refers to a change in the phenotype caused by a change in the genotype, while plasticity is any change in the phenotype without a change in the genotype. Today, I'm going to talk about something called developmental phenotypic plasticity, which is the influence of the developmental environment on the mature phenotype, but there are a host of other types of plasticity that are important. And then finally, there's a fun twist in all of this, which is that plasticity itself can differ between populations. Right? The magnitude of the phenotypic response to different environments can change between populations. So there's a lot going on here. I'm going to use a reaction norm later on in order to look at these kind of three components. So we're going to walk through what we expect to see now. If we have a population that performs differently based on developmental temperatures, right? There is some effect of developmental phenotypic plasticity. We'd expect a reaction norm with a slope that's different from 0, whether it's positive or negative. We can add a second population into this reaction norm for comparison. You can see that the effects of genetic differentiation within the developmental temperature would result in these vertical differences in the reaction norm, but genetic differentiation can also change the slope of the reaction norm itself, thereby affecting the magnitude of phenotypic plasticity. All right, so this is what I'm going to talk about today, that looking at how the effects of these different adaptive mechanisms are patterned across large spatial scales. In order to do that, we need a good model system. This is where the copepods come in. Copepods are abundant animals. If you don't know about them, you've swallowed them. If you've ever swallowed a mouthful of seawater, they're the most abundant animal in the ocean, not on the planet. And that makes them exceptionally ecologically important, but it can also make them really good model systems for studying adaptation to different environments. This is the species that I work with, Acacia tansa. It's a species that dominates coastal and estuarine systems around the world. In the North Atlantic, where I've been working, it has a geographic range that covers this large latitudinal thermal gradient. And then finally, and importantly, we can raise it in the lab fairly easily. So we can bring it in from these diverse field conditions to the lab and raise it for several generations before and during experiments. So the first chapter of my dissertation started off with kind of two general questions or general goals: to examine the spatial patterns and the effects of genetic differentiation and phenotypic plasticity on thermal tolerance, and then to look at these patterns and see if we can't disentangle the effects of selection by the environment and gene. So the first thing we had to do was go out and collect populations of partial constant from across this large environmental gradient. So I converted a rental car into a mobile plankton lab. It's a lot less exciting than it sounds. But with that, I was able to drive up and down the East Coast, collecting these live populations and keeping them happy and healthy until we got them back to the lab. We ended up with 10 established in our lab, ranging from the Gulf of Mexico down into the Florida Keys, up the Atlantic coast into the Bay of Fundy, and I'll talk about one northernmost population today from Prince Edward Island in Canada. Each live culture started with over 1,000 mature females and abundant males, and in addition to those individuals, I collected and preserved samples for later genetic analysis. So we have some good representation of diversity in the field at each of our sites. Everything back in the lab, then spent 2 generations under constant conditions to minimize effects of previous environmental acclimation. And then we ran all 10 populations through a split brood common garden experiment, where we collected eggs from the egg 2, split them into 2 groups, which developed at 2 different temperatures, 18 and 22 degrees, I think for a couple different reasons. We then exposed mature adults, once they had finished developing, to an acute heat shock and used individual survival data from those heat shocks to estimate thermal performance. Because of our experimental design, differences between populations within the developmental temperature should reflect the effects of genetic differentiation on thermal tolerance, while differences between the curves of the 2 developmental temperatures within a population should be due to developmental phenotypic plasticity. In the end, over 6,100 individual copepods fit into these curves, which look something like this for one population. The stress temperature on the x-axis, survivorship. These individuals survived, these did not, and we fit logistic regressions to the data for both developmental temperatures. Now, 2 curves per population, 10 populations, 6,100 individual data points. The full figure is a lot to take in, and so instead of showing that, I'm going to boil everything down even more to 1 number per curve using LD50. So this is a common metric for thermal tolerance. It's just the temperature at which we'd expect to see 50% survivorship. And so by estimating LD50 for both developmental temperatures, we get some idea of how developmental phenotypic plasticity changes the performance curve. And we quantify that as delta LD50, just the difference between the 2 thermal tolerance of the 2 developmental temperatures. And all of this can be represented in a reaction, like I mentioned earlier. We have developmental temperature on the x-axis, thermal tolerance on the y, and we can use this to look at the effects of genetic differentiation and phenotypic plasticity on thermal tolerance. Starting off with genetic differentiation, we see very clearly that within developmental temperatures, there is an effect of genetic differentiation. Right? Our southernmost population has the highest thermal tolerance, our northernmost population has the lowest thermal tolerance. There's some variation in between, which we'll get back to in a second. We also see a significant influence and a significant effect of developmental phenotypic plasticity. Right? By increasing developmental temperature, thermal tolerance increases in all populations. But it increases by different amounts. Right? So some of the slopes of these reaction arms are different. Our northernmost population, for example, has a much steeper reaction arm than some of our southern populations. So a big chunk of this chapter of my dissertation then looks at this variation and tries to explain it from an environmental relation perspective. Right? So we have climatologies that I built for all 10 sites, and with those we can test things like the climate variability hypothesis, and how it relates, or how it, as opposed to Stillman's hypothesis about the physiological trade-off between plasticity and the evolution of thermal tolerance. Our data actually supports the Stillman hypothesis, but I'm not going to talk about that. If you're interested, help me down later. Instead, I want to shift our attention away from where things are different to where they're not different. This is thermal tolerance plotted against latitude of origin, so where I collected the copepods from. And we can see this really clear and striking lack of differentiation of thermal tolerance over a large portion of our sampling range. To put this into perspective, these populations were collected from the Gulf Coast, the Gulf of Mexico, the Atlantic coast of Florida, Connecticut, Maine, and Canada. Right? right? Drastically different thermal environments. And so this was really surprising. This isn't what we expected at all. And so the unexpected direction that this chapter went in was asking why. Why don't we see differentiation of thermal tolerance over this range? And we came up with sort of two hypotheses that this could actually reflect the effects of selection, that despite the differences in the thermal environment, selection favors a generalist, or that this reflects constraint by gene flow, that over evolutionary timescales, gene flow is strong enough to prevent the adaptive divergence of thermal performance curves. If you remember the title of my talk, you know what direction this is going in. But in order to sort of try to tease these apart, we went back to those samples for genetic analysis. This is the haplotype network we get from a couple hundred individuals that we sequenced CO1. For those who aren't familiar with haplotype networks, each circle represents a unique sequence. The size is proportional to the frequency with which we observe that sequence. And then the color indicates which geographic site we collected that sequence from. And there's a couple things that stand out. First, 4 distinct clades, which I've creatively named A, B, C, and D. And these clades are all widely distributed, right? For example, clade C is recovered from sites in Florida, Connecticut, Maine, and Canada. The same is true for the rest of them to some degree. In addition to that, we've recovered several widely distributed haplotypes, where the identical sequences were recovered from sites separated by large distances. This one, for example, is from Connecticut and the Gulf Coast of Florida. This one from the Atlantic coast of Florida and Maine. All of this is strongly indicative of gene flow or connectivity over some time scale. But our real support for the statement that gene flow constrains adaptation is what happens in these populations outside of the box, where we do observe differentiated TPCs. Those populations tend to be characterized by a single dominant haplotype, which isn't shared in the population. And then finally, interestingly, what we see is that this tells us that local adaptation to the thermal environment occurs within clades. So when gene flow or connectivity weakens, adaptation to the local thermal environment can occur relatively rapidly and repeatedly in this species. So to wrap up quickly, we found strong divergence of thermal tolerance and plasticity over large spatial scales. However, we also see this remarkable lack of divergence in populations collected from very different thermal environments. And then by integrating in information from molecular ecology, we suggest that this is due to constraint by gene flow rather than selection for generalist. And all of this highlights that understanding patterns in adaptation and diversification requires an integrated approach if we want proper, robust interpretation and application of this understanding. With that, I'd like to thank a bunch of people. The preprint is up on bioRxiv. We're hoping to see the manuscript actually published by the end of the summer in global change biology. I will take any questions. Yeah, so this was